Okay, we've been talking about the elements of weather, and to review very briefly, we discussed temperature initially, and then pressure and wind. And I mentioned the fact that it's extremely important that we integrate these elements, that is temperature, pressure, wind, and what we're going to talk about tonight, moisture. Of course, I realized we dealt with moisture a little bit last week, but we're going to deal some more with moisture tonight and try to integrate all these things together. And so we're going to basically follow the approach that I have on the board, going from 1 to 4. And much of this is review. And keep in mind that, as I mentioned, while next week we will not be here, and the week after we will review your exercise 2 part 2, which deals with this. The following week actually is the exam week. And so we have 2 more, or at least 1 more session, 1 more class session before the midterm examination. And so while we're away next week, the following week, when we submit this exercise 2 part 2, we will go over that exercise as well as exercise 2 part 1, and we'll also review for the midterm examination, which will be the following week. So this is just to give you some perspective as to what we'll be doing the next few weeks. In the meantime, of course, what you need to do is continue to read all of Chapter 3, the chapter on weather, and especially the first part of that chapter dealing with weather, and we'll be talking a little bit about climate also. But what I'd like to do tonight, again, is to talk about the adiabatic rate, the adiabatic heating and cooling, and again, to give you this information that's on the board to explain what we're talking about as far as adiabatic heating and cooling. Just to review briefly, last week we talked about moisture in the atmosphere. Moisture is always in the atmosphere. Right now, water is in the air in a gas state in the form of water vapor, and it will continue to be in this state until the air gets cool enough where it condenses out. And at that point, we will in fact have condensation and cloud development, as we talked about as far as the hydrologic cycle. And then we will get some kind of precipitation, whether it's rain, sleet, snow, or hail, which is largely dependent on the temperature. Now, moisture basically is released in the atmosphere, as I said, when the air cools off. So there is a specific relationship, as you found out in exercise 2 part 1, between the amount of moisture in the atmosphere and the temperature of the atmosphere. Now, the air cools off, and we talked about the fact that in the troposphere, the air cools off at a rate of 3.5 degrees Fahrenheit per 1,000 feet. So for every 1,000 feet that the air rises, the temperature will go down on the average at 3.5 degrees Fahrenheit. We call this the normal or the average lapse rate. The normal or the average lapse rate assumes no movement of air. It simply says that the further up we go from the Earth's surface, the air will cool off on the average at this rate of 3.5. So you need to remember 3.5. Now tonight we'll be talking about something a little different. We'll be focusing upon the air moving instead of staying still. Now, we've already talked about the horizontal movement of air, which is wind, and it's a result of the pressure gradient force affecting air movement from high pressure to low pressure. But It's also important to keep in mind that in particular areas, especially in strategic degrees of latitude, as we talked about, such as the equator, 30 degrees north, 60 degrees north, and especially at the equator at 60 degrees north, you have air coming together, converging, and rising up. And we found out that at the equator, the air cools off as it rises, and eventually it reaches the dew point, and as a result, we get a lot of rainfall at the equator. As a matter of fact, along the equator, you have some of the wettest weather in the world because of convergence and low pressure, and also the abundance of moisture in these very low latitudes. The same thing happens at 60 degrees north. The difference is that at 60 degrees north latitude, where we're affected the most, this converging air between the westerlies from the southwest converging with the polar easterlies from the north, it results in very unstable atmospheric conditions. And as a result of this convergence, this is not the case along the equator. Along the equator is very mild. As a matter of fact, it's fairly stable, even though you have this convergence. But at our latitude, the air rises quite a bit, oftentimes on its own, primarily because of it's heated. And warm air is very buoyant. It rises very easily. And as the air rises, it cools off. And as the air cools off, it will eventually get to the point where it cannot hold any more moisture that's in it. And in other words, it will reach the dew point. And at this point, you will have condensation, precipitation of some kind. Now, over here, number one, it deals with the various methods or manner in which the air rises. One way is convection. Now, in convection, as you all know, I hope it's in the textbook very clearly mentioned by the author, that convection is the fact that you have very warm air being buoyant and rising up. For example, let's say that at the surface you have general air temperatures of 50 degrees Fahrenheit. But for some reason, you have the air being heated to 60 degrees Fahrenheit. Well, this particular area of air obviously is much warmer than the air around it, and so we can differentiate between heated air on the one hand, the air that's been heated 10 degrees warmer than the surrounding air, and in fact the surrounding air, which is 10 degrees cooler. This air is 60 degrees Fahrenheit, the air around it is only 50 degrees Fahrenheit. And so basically this heated air will act as a like a bubble in water. It will rise, and as this heated air rises up, it will cool off. And again, as suggested in the hydrologic cycle, the air will cool until it reaches the dew point, and that's when you will have condensation. Well, this is convectional rising of air. This is one method in which air rises and cools off. Now, I mentioned that we'll be dealing with adiabatic heating and cooling. Adiabatic heating and cooling. And I don't have this written on the board, but basically, this is what we're dealing with. Adiabatic heating and cooling. In other words, it's a description of the manner in which air cools off as it rises up, regardless of the reason how it rises. Here we know it rises because it's warmer than surrounding air. Now, as the heated air rises up, in the case of convectional rising of air, as I said, it will cool off. And what we can determine is the temperature of this rising air at various elevations. And so, as the air rises up, we can determine the air temperature at 2,000 feet. And the air temperature as it rises to 2,000 feet becomes 49 degrees. As it rises up to 5,000 feet, it becomes 32.5 degrees. Now, it rises and cools off at what we call the adiabatic rate. That is the dry adiabatic rate. The dry adiabatic rate, specifically, is 5.5 degrees Fahrenheit per 1,000 feet. This is the dry adiabatic rate. This is the rate of cooling on the average of air as it rises up from the Earth's surface. So, if we realize that for every 1,000 feet the air will cool off at 5.5 degrees Fahrenheit on the average, then we could very easily determine the temperature of the rising air at 2,000 feet or at 5,000 feet. It's a very simple procedure to find out the temperature of rising air at these elevations. And it's very important, of course, for you to remember the procedure. And this is the procedure. If you want to find the temperature of rising air, for example, at 2,000 feet, you take the elevation, you multiply the elevation in decimals, 2.0 or 2, times the dry adiabatic rate. The dry adiabatic rate is 5.5 degrees Fahrenheit per 1,000 feet. And so this will give us 11. In other words, the temperature at 2,000 feet, the temperature of the air that was heated to 60 degrees Fahrenheit is 11 degrees cooler at 2,000 feet than what it is at the surface, where it's 60 degrees. And so in order to find the temperature at 2,000 feet, you simply subtract 11 from 60, okay, and you get 49 degrees. And so this is the basic procedure of determining the temperature at whatever elevation, if you have a certain temperature at the surface, in this case of the rising air. If we wanted to determine the temperature at 5,000 feet, the only thing we would do would be to change this to 5, and we would multiply 5 times 5.5, and it gives us 27.5, and which tells us that the temperature at 5,000 feet is 27.5 degrees cooler than what it is at the surface, where it's 60 degrees. So therefore, in this case, we would subtract 27.5 from 60, and that will give us 32.5. And I believe that's correct, so 32.5. So you do it the same way. And anytime you want to find the temperature at any elevation, if this was a decimal, for example, if we wanted to find the temperature at 2,500 feet of the rising air, again, we're multiplying a decimal, 2.5 times the, actually 2.5 times 5.5, 2,500 feet times 5.5, and whatever we get, we subtract from surface temperature. And you do it the same way. So you do it whether you have a fraction or whether you have a whole number. So do you all have any questions about how you get the temperature of rising air at some elevation if it rises from the surface and has a certain surface temperature that's warmer than the surrounding air? Okay. Have any questions? You can ask questions.
So if it was just 500 feet that we need to find out, we would multiply 5.5 times 0.5?
0.5.
Okay.
Yeah. So that's it. Okay, so that's all you do. Now, it's important in looking at adiabatic heating and cooling, really to look at the concept as well as the computations. The concept is the fact that, and we've already talked about this, and I don't want to be redundant, but when air is heated, for whatever reason, it's going to rise because you're going to have heated air, it's going to be warmer than surrounding air. You might ask the question, well, what instance does this take place? What's an example? Well, in the Pacific Ocean, as an example, you have the Hawaiian Islands. And it's a fact that land areas heat up a lot quicker than water areas. And they also cool off a lot quicker than water areas. But what happens, especially during the summer, when solar radiation is very direct, the land surface on the islands heats up very, very rapidly, and much more so than adjacent water areas in the surrounding Pacific. In other words, the air above the islands is much warmer than the air over the ocean. And so what happens is that the air over the islands rises up more rapidly than the air over the ocean, because the air over the ocean being more stable, you're not going to have that convectional rising. But anyway, as a result of the air rising over the islands, you're going to have air cooling off, and you're going to have condensation, and as a result, you'll have cloud development over these islands and other islands, because land areas are much warmer than adjacent water areas. You're going to have this convectional rising of air. So if you were in an airplane flying over the Pacific Ocean, and you were to look down, especially during a very warm summer day, chances are you would see a lot of clouds over these islands as a result of a convectional rising of air, because of the heated air over the land area. So this is one example of air being heated as opposed to surrounding air not being heated. That's the theory, that's the concept. That's the theory, or the concept. The computations, I think, are pretty straightforward. Okay, that's one thing. The second thing you need to keep in mind as we talk about adiabatic heating and cooling is the fact that we have to consider the surrounding air. And the surrounding air in this diagram is is represented by these numbers: 50 degrees at the surface, 0 feet. 2,000 feet is 43 degrees Fahrenheit, and 5,000 feet is 32.5 degrees Fahrenheit. Well, you might ask the question, well, how do we arrive at these temperatures? Well, actually, you do it the same way as you arrive at these temperatures of heated air that's rising up. You do it the same way. In other words, for example, if you wanted to know the temperature at 2,000 feet, you would multiply 2 times, not 5.5, because that's rising air. You would multiply 2 times 3.5, because the surrounding air does not imply atmospheric rising. The air is stable. All we want to know is what is the temperature at 2,000 feet. And so we multiply 2 times 3.5, which is the normal lapse rate, and we get 7, and we subtract 7 from 50, which gives us the 43 degrees. And you do the same thing. You want to know the temperature of the surrounding air at 5,000 feet. You multiply 5 times 3.5 and subtract from 50. So in this exercise you'll have to determine the temperature at various elevations between rising air and surrounding air. And that's why I'm emphasizing this, because you're going to have some time to work on it, but it's very important that you understand it. So are there any questions as far as the difference between stable surrounding air that does not rise and which we use the normal lapse rate to figure out temperatures at various elevations, and the heated air, which has been heated as a result of some factor, and as a result it rises up and cools off at the adiabatic rate, which is 5.5 degrees Fahrenheit per 1,000 feet. The computations are the same between the dry adiabatic rate and the normal lapse rate. Okay, now, that's fairly basic, but we need to keep in mind that this assumes that the air is dry, and there's a problem with this because we know that the air always has a certain amount of water vapor in it. It might be 2 grains, it might be 1 grain, it might be 10 grains. And we know also as the air cools off, this water vapor eventually will condense. It will change from a vapor to a liquid. Primarily, clouds will develop and you will have precipitation. So, let's consider another way in which the air rises and cools off. We've already considered one way, that's convectional rising. But of course, there are 2 other ways that we've talked about, I believe. I think we talked about this last week. Frontal and orographic. Now, frontal, very briefly, is when you have a cold mass of air coming in like from the North Pole area. It's much colder than the air in front of it. It's warmer air. And what happens is that the warm air is pushed up and over the front edge of the cold air. And as the warm air is forced to rise, as what happens with convectional rising, the air cools off, and eventually the water vapor condenses to the dew point, or at the dew point, and you have condensation. And a couple of weeks ago, as a matter of fact, we had a cold front pass through the area, and it got very, very cool. I think it was not this past Friday, but Friday before last. I believe Thursday it was like 90, 92, 93 degrees. And then on that Saturday, or maybe the following Sunday, temperatures got down to 65, 70 degrees as a high. So we have these cold fronts come into the area, especially this time of year. But when you do, the cold air forces the warm air up, it rises, it cools off, and you have the same effect. Now, the third way that the air rises and cools off and reduces the likelihood of some kind of precipitation is orographic. And this is what we want to focus on tonight, orographic. You have a mountain barrier affecting the horizontal flow of air. And so, for example, we've already talked about, as I said before, air moves from high pressure to low pressure, horizontally, creating wind. But obviously, if you have a barrier, such as a mountain in the way, the air will be forced up vertically over the mountain and back down the other side, where you're going to have the same effect as far as atmospheric cooling. So, let's look at what happens, though, if you have a little bit of water vapor in the air instead of not having any water vapor at all in the air. Let's say you have just a little bit, 1.9 grains of water vapor, not a whole lot. With this amount of water vapor in the air, a temperature of 30 degrees Fahrenheit is needed for condensation. It has to get very, very cold in order for this small amount of water vapor to condense out of the atmosphere. Okay, so let's do some problems. If I were to ask you what is the temperature at 2,000 feet, how would you go about doing this, and what would be the answer? And those of you with maybe a calculator can do this fairly quickly, or even by hand, if you go through the procedure that we went through a minute ago. What would be the temperature at 2,000 feet? Quick calculation. What elevation would we, what would we use? What would we multiply?
You're using 60 as your...
16 is the air temperature at the base of the mountain. And we're going up 2,000 feet. What is it? 53? Who would agree with that? Who would disagree?
I agree.
You agree?
Yeah, that's fine. You use 3.5 as your normal lap rate, right?
Yeah, but we're not using 3.5
Why wouldn't you?
because the air is rising up. What do we use when the air rises up? We use 5.5. When the air rises up, we use the dry adiabatic rate, which is 5.5. See, the air is forced to rise up. And so we use the 5.5. Remember, rising, unstable air, we use the dry adiabatic rate. If the air is not rising, no indication that the air is rising, we use the normal lapse rate, which is only 3.5. See, the suggestion here, actually the indication is, that the air is rising up. And so we have to use 5.5. Okay, that's the only thing, the only way I think you went off base here, and that is you use 3.5 instead of 5.5. You multiply this by 2, right? And you get what? You get 11. Is that right? We just did that, right?
Yeah.
And 11 from what? From 60. Gives you 49 degrees. Okay, what would be the temperature at 5,000 feet? What would be the temperature at 5,000 feet? Now don't be gun shy because you got...
Well, see, that's why you said before I remember you saying that it was rising. Before all I heard you say was what would be the temperature at 2,000 feet. So I assumed we were talking about stable air. That's why I did it that way. So I'm not saying anything now. So
It would be 32 more times. When you got it on board, 32.
So what now?
32 more times. Yeah, 32.
Okay, yeah, 32.5 then. But you know how to get that though, right?
Yeah.
But,
Now, going back down, would you use that one?
no, well, you use 5.5 going back down, but what would you multiply 5.5 by going back down?
The negative one?
This is 5,000 feet. So we use 5,000 feet, right? Okay, 5 times 5.5 is what? 27.5. So what would we do with the 27.5? We would add, we would add 27.5 to the 32.5, which would give us the 60. Would give us the 60. And we would add, we'd do it the same way. We're dealing with the dry adiabatic rate, but see, when the air is going down, it heats up. So after we do the multiplication, instead of subtracting, we add on to the number up here. But again, getting back to the question that you raised, just keep in mind that when you're dealing with stable air, you use the normal lapse rate, which is 3.5 degrees Fahrenheit per 1,000 feet. When the air is rising for whatever reason, if it's forced to rise over a mountain, if it's heated more than surrounding air and rises, you still use the 5.5. And you go about doing it the same way. Any other questions? No questions on this? Okay. Well, let's move on to the last situation. Now, this situation, I think, is the most interesting because we're working with more water vapor. Here, we were working with 3 grains of water vapor. Over here, we were working with only 1.9 grains of water vapor. And you would notice that here, with 3 grains of water vapor in the air, the dew point is 43.5 degrees Fahrenheit. Now, this has a conceptual aspect to it, simply because the more water vapor that you have in the air, the temperature does not have to get as low for the water vapor that's in it to condense out. If you have a lot of water vapor in the air, then the air does not have to get so cool for that water vapor to condense out. If you only have a very small amount of water vapor in the air, then it's going to take a very low temperature for it to condense out. So generally speaking, the more water vapor you have in the air, the higher the dew point. The dew point here is 43.5 degrees Fahrenheit. And so let's do some problems here. And hopefully this will be fairly clear, because this is the last one that we'll be dealing with. You all know how we will get the temperature at 3,000 feet. Now, I know it's already stated right here, but how would we get it? We would multiply what by what? 5.5 times 3. It gives us 15, 16. Is that right? And we would do what? 16.5? From what? 60. And it gives us the 43.5. 43.5. Okay, that's pretty straightforward. Okay, but something happens at this particular elevation. Something happens at this particular elevation. What happens at 3,000 feet?
Saturated, whatever.
Right, the air becomes saturated. Remember last time we talked about
Can't hold any more water vapor.
can't hold any more water vapor, but the air is saturated. The relative humidity is what? 100%. You know, remember the glass, you know, you keep lowering the glass with the same amount of water vapor in it, you know, and when the temperature gets so low that it can't hold any more water vapor, you're going to have precipitation. Is that what you're going to have?
Yeah.
No. You have cloud development. You have cloud development. The water vapor will condense around the dust nuclei in the air. And of course, all of these billions and billions of dust nuclei, the water vapor condensing around these dust nuclei. And what you have is a cloud. Now, does the air continue to rise, or does it stop rising at this point, at 3,000 feet? What happens to the air? Does it continue to rise? I would think so, right? Well, yes or no? What would you say? It would, right? Air will continue to rise from 3,000 feet. How far do you have to go from 3,000 feet to the top of the mountain? You have to go 2,000 feet. So how would you determine this? I mean, you can tell this just by looking at it, but how would you figure out the distance that you would have to go from the dew point elevation to the top of the mountain? What? Well, let me phrase it another way. How would you determine how far you have to go in thousands of feet? If you're at 3,000 feet, the dew point elevation, and you want to know how far you have to go to the top of the mountain, what would you do? I mean, you indicated that it's 2,000 feet, right, between here and the top of the mountain. Well, how did you get that? Okay, subtract 3,000 feet from 5,000. Now, this is pretty obvious, but you may get some problems where it might not be so obvious, but you'll have to remember that in order to determine how much further the air has to rise going up and over the mountain, you'll have to subtract the dew point elevation from whatever the elevation is at the peak of the mountain. atmosphere, in this case 5,000 feet. So you subtract 3,000 from 5,000, you get 2,000. Now this is important. This is extremely important, simply because the air is continuing to rise up and over the mountain. And so it's going to continue to cool off, because rising air cools off. But it's going to cool off at a different rate. From here to here, the air cool off at what rate? At the dry adiabatic rate. That's what we use. At the dry adiabatic rate. And the dry adiabatic rate is 5.5 degrees Fahrenheit per 1,000 feet. As the air continues to rise above the dew point elevation, it's no longer dry. Where it's dry down here, up here it's not dry. It's still rising up and over the mountain. It's forced to rise up and over the mountain. But it's not dry, it's wet. It's wet air. And wet air cools off at a different rate than dry air. And specifically, that rate is 3.2 degrees Fahrenheit per 1,000 feet. 3.2 degrees Fahrenheit per 1,000 feet is the wet adiabatic rate. Now, we might ask the question, well, why is the rate less than, say, 5.5 degrees Fahrenheit per 1,000 feet as it is with the dry adiabatic rate? Well, you remember that the air is releasing moisture. The air is releasing moisture. Remember that the air has 3 grains of water vapor in it. And so this water vapor is being released into the atmosphere. When water vapor is released into the atmosphere, the heat that was needed to evaporate this water in the first place is released back into the atmosphere. And as a result, the atmosphere is not as cool. And so when this moisture is released, the air is not as cool. It cools off at a lesser rate, and this lesser rate is 3.2 degrees Fahrenheit. Now, as the air moves from here to here, we have to realize how much further it's going to rise up if we want to know the temperature up here. Now, I've written it up here, if you can see it, 37.1. That's the answer for the top of the mountain. But if I were to ask you, how would you get the temperature at 5,000 feet, then you would do it the same way as you did before. You would multiply 2, because the air has to rise up another 2,000 feet from here to here. We would use what? What would we use? 3.2. Use 3.2. You would get 6.4. In other words, it's going to be 6.4 degrees cooler at 5,000 feet at the peak of the mountain than it is at 3,000 feet, where it's 43.5 degrees where the dew point is. And so you do it the same way as you did before. You subtract 6.4 from what? 43.5, because this is where we're at. 43.5. Okay, and you would get 37.1. So when you get your exercise, keep in mind that you, when you get to the dew point elevation, number one, you have to find out how much further up you have to go. And in order to do that, you simply subtract the dew point elevation from the peak of the mountain, whatever the peak of the mountain might be. Then once you get that, you have the elevation from which to multiply times the wet adiabatic rate, because the dew point will have been reached, in this case 3,000 feet. Now, so it's going to be wet all up in this area. Now, as the air descends back down the other side of the mountain, what happens is that the air basically loses all its moisture on this side, the windward side. This is the windward side. Over here is the leeward side. And in other words, it's dry on this side of the mountain. And so how would we go about figuring out the temperature at the base on the other side, where it's 65 degrees? Same way we did before, right? From here to here, how far? 5. So we multiply 5 times what? 5.5 because it's dry. And we get, let's see, 27.5. What will we do with the 27.5? Add it to the 37.1, we get 65 degrees at the base on the other side. Okay. Okay, any questions? Any questions on that? Okay.